Today we're going to do chapters 6 and 7. These are both little strange chapters. Years ago I told McMurry not to take 6 out. It was just silly. So, but he wanted to give an overview of reactions, basically to establish the nomenclature. And then we're going to do chapter 7, which is the introduction to alkenes. And we'll talk about the ionic addition of halogen acids to alkenes. It's our first reaction. When we hit chapter 8, we are going to start reactions, big time. This can be a little scary. If you want to like read ahead or look ahead or something, there will be lots of reactions that you have to master. But okay, let's go ahead and start with chapter 6. Basically, these are the broad categories of reactions we're going to deal with. Addition reactions. We're going to take 2 molecules, going to add them together to make something. Elimination is just the opposite of addition. We're going to take 1 molecule and break it down to 2 or more. Substitution, we will exchange parts from one molecule to another. And finally, rearrangement. These are really fun, but you really can't do much with rearrangements until maybe next semester. But they're really challenging and fun. A molecule just undergoes a change in its connectivity. That is, it goes to an isomeric form, for example. In addition, reactions. This is the example we're going to talk about today, both in this chapter and again in chapter 7. In addition reaction, we're going to combine things together to make 1 molecule. This is an alkene. You recognize that. Carbon-carbon double bond. This is not ethylene. It is ethene. Ethylene is a trivial name. And it will add something like a halogen acid, HBr, HCl, HI. And the product is an alkyl halide of some sort. Essentially, we're adding hydrogen to 1 carbon and the halogen to the other. We'll talk about this in detail and look at the mechanism of this reaction so we can predict the products. Eliminations are just the opposite, like I said. This, of course, is ethanol. In an elimination reaction, we're going to remove something from a molecule, just the opposite of addition. Here we're going to take ethanol, we're going to remove the water, be an acid catalyst for that, and here we make an alkene. Again, if you looked at it backwards, it would be a simple addition reaction. Substitution. We're going to take and we're going to swap parts between different molecules. The substitution that we're going to talk about today is, it's free radical halogenation. In organic chemistry, in the process of teaching organic chemistry, this particular reaction has a long history. This is actually a really lousy reaction, okay? Really lousy reaction, something that you would virtually never do in the real world. But many years ago, 2 gentlemen came up with a new strategy for teaching organic. This was Morrison and Boyd. And their book was revolutionary. And they wanted an example of a substitution reaction. And so they picked this one. So this was the very first thing that showed up in the book, the first reaction everyone learned. And they, of course, all assumed it was the most important reaction in all of organic chemistry. And it, of course, it's not. But we'll talk about the steps of this, and then later on we'll talk about why it's not such a very good reaction. Here what we're doing is we're going to form radicals from the chlorine. Radical is going to abstract a hydrogen, make a carbon radical, which adds the chlorine, liberates an HCl. It's a radical chain reaction. And finally, an example of a rearrangement. In a rearrangement reaction, we're going to take, there we go, we're going to take this, in this case it's an alkene. We're going to put this in the presence of an acid catalyst, and we are going to make an isomeric alkene. So 1 butene, and this is 2 butene. We'll talk about nomenclature today as well. Mechanisms of these are very interesting and can be very challenging. You can get fantastic skeletal rearrangements. And one of the great exercises, fun exercises, is to try to figure out the pathway of all the transfers that happen that allow you to go from one spot to another. All right, when we speak of reaction mechanism, what we're going to do is keep track of electrons and atoms. There are two ways that we can break bonds in carbon compounds. One is homolytically, and this is going to take a covalent bond. Each atom in the covalent bond will take one electron and will form a pair of radicals. This is what we'll do in the free radical halogenation. We can also do what's known as a heterolytic cleavage. This is more common, actually more useful. And in this case, we're going to take a full pair of electrons, transfer them to one atom. That's going to leave us a positive species and a negative species. We show the movement of these electrons using these little curvy arrows. They are officially called curvy arrows. And if you note, they are different for a homolytic and heterolytic process. When we do this, well, I guess I was supposed to do that. Okay. When we use our, or show a homolytic process, we use an arrowhead with only one little spike on it. That shows you what we're dealing with is only a single thing. Okay, let me just back that up, sorry. That didn't work quite right. For the heterolytic process, we use a full arrow, and again, it's supposed to start at the electron pair you're moving and go to the destination atom. This is how we'll do electron bookkeeping.
Do we have to always start from the top when we're doing that?
No. Any way you get them to work. All right, let's talk about our homolytic free radical chain reaction. And again, we're going to simply do the free radical halogenation of methane. Very simple reaction. A free radical chain reaction involves 3 steps. We're going to do initiation, a propagation step, and a termination. A very classic question on an exam is you would be given something, given a molecule, and you would be asked to show for a free radical reaction the initiation step, a full set of propagation steps, and some possible terminations. So this is a classic exam question. So make sure that you get these. It's not complicated. The reaction we're doing is this. Once again, we have methane. We're going to take chlorine. Usually we need light or something as a catalyst. And we're going to make chloromethane and HCl. The initiation step in this reaction. What we're doing is taking light energy. The chlorine-chlorine single bond is absorbing that energy. And when it does, it splits. into two parts. Both of these are chlorine atoms. Very, very simple reaction. Whenever you have an atom like this, it's called a radical, a free radical. They're very, very reactive. This chlorine only has 7 electrons around it. Of course, it dearly wants 8. And so radical reactions tend to go very quickly and very non-selectively. Because it wants it so badly, it will just grab it from anything. Propagation. Propagation is a little more complicated. When you write a set of equations for propagation, you have to remember that you're going to take the radical that you started with here, and you're going to wind up with that very same radical at the bottom. This is why this is a well, I just lost the word, but in this free radical reaction, we have made the chlorine radical. That's in our initiation step. Like I said, this is a very reactive species, and it will encounter a methane. And when it does, it will literally yank a hydrogen atom off of it. When it yanks the hydrogen atom off, it's going to leave behind a methyl radical. Methyl radical, and we have formed 1 mole of HCl. Now the methyl radical is even much more reactive than the chlorine radical. And there are lots of things that it can do, but the thing it is most likely to do is to find another mole of chlorine. It will then abstract a chlorine atom from Cl2. When it does, it forms the product chloromethane and reforms the chlorine radical. This is a chain reaction. That's the word I was hunting for. This is a chain reaction. So once we make the chlorine radical, the whole process starts again. If you think about this in terms of simply adding up the equation, the net equation, chlorine radicals would cancel, methyl radicals would cancel, and you would simply have methane, chlorine, HCl, and the product chloromethane. So this is the free radical chain reaction. Termination. Termination simply means we stop the free radical chain process. We can do this any way. One possible way, what if a methyl radical happened to hit a chlorine radical? We would form methane, but we're out of radicals now, aren't we? So we have terminated the chain process. 3 steps, they're not difficult. These are other possible termination steps. 2 chlorine radicals can simply get back together to make molecular chlorine. This is the one we just saw, chlorine plus methane, methyl radical to give chloromethane. Or we can even take 2 methane radicals and make ethane. Overall, initiation, make radicals, usually using something like white. Propagation, take a radical, wind up with a radical, and we make our mole of products. And finally, termination. Any of the termination steps will certainly work. Now, this reaction has problems. Chapter 10, I believe, will talk about free radical processes in much more detail. But the reason that this has problems is that once we make this product, chloromethane, this chloromethane molecule actually forms a more stable radical than methane would. So energetically, the chlorine radical that we're producing is more likely to react with this. And that then would give us dichloromethane. Dichloromethane, in fact, forms a more stable radical than even chloromethane. And so we would form trichloromethane, and finally tetrachloromethane. If you have a molecule that's not as simple as methane, because radicals are so reactive, they could grab a hydrogen from anywhere on a molecule. So you can get lots and lots of isomers. So in general, it's a nice simple reaction, but not useful synthetically, because unless you want to make carbon tetrachloride, it's really not useful synthetically, because in most cases you would get bad mixtures of products. Bottom line for this chapter, do familiarize yourself with these steps and understand the basics of the propagation step. Start with a radical and end with a radical. Any questions? The next set of reactions, this is a substitution reaction that's much more useful than simple free radical halogenation. These are going to be reactions involving polar covalent bonds. And we talked about the fact that many molecules form polar bonds due to differences in electronegativities. This is chloride anion. In this type of a substitution reaction, this is going to seek out a positive center. Because of that, it is going to be called a nucleophile, nucleopositive loving. This is electrostatic potential map for chloromethane. If you look at the map, and not surprisingly, the chlorine being much more electronegative sucks the electrons down towards itself and leaves the carbon here electron deficient. This is going to be called the electrophile, the electrophilic center. This means that it is seeking electrons. In this type of a substitution reaction, what's going to happen is the nucleophile is simply going to attack the electrophile, and we're going to have a leaving group. So those are the three things that we talk about. Here's how we would represent this thing. This is our nucleophile. Here's our electrophile. If we want to show the flow of electrons, we would make our arrows start here and go to the carbon. That would put too many bonds around this carbon, so the bond to this chlorine must break. When it does, we would reform a different chloromethane, and this would be our leaving group, the chlorine that was here. So this is a substitution reaction. We will call this a substitution nucleophilic bimolecular, or SN2 reaction. In an SN2 reaction, we have a nucleophile attacking an electrophilic center. The bond to the leaving group breaks, forms a product, and here's our leaving group. Now there's a very, very nice little movie that shows this. This, again, is a calculation. Here's our nucleophile, here's our electrophilic carbon, and here's the leaving group. Now, it's symmetrical reaction here, so this thing just goes back and forth and back and forth. And as it does, what I'd like you to do is to look at what happens to this carbon in the middle. Here in the middle, the absolute middle, where we have partial bonds to both, this is planar, isn't it? It's planar. Now, just use your imagination and pretend that we're in chapter 9. If this was a chiral carbon, as this thing goes planar and then flips to the other side, what have we done? Well, we've gone from R to S, haven't we? So we'll talk a lot more about this. It's actually a very interesting reaction and very useful in organic chemistry. All right, let's return to our ionic addition reaction. Here we have, instead of ethene, we have propene, 3 carbons with a double bond. When we do this reaction, the product that we get is 2-bromopropane. This is essentially the only product that we're going to get. Now, if we put the bromine on this carbon, that would give us 1 bromo with it. But we don't get that. 2-bromo product is virtually the only thing that we get. So we're going to explore this reaction in terms of what the mechanism is and why in the world we only get 1 product when we might expect 2. We'll look at it briefly here and then do it again in much more detail in the next chapter. The very first thing that's going to happen in a reaction like this, we have a very strong Bronsted acid, and we have our alkene. Remember what we said about the pi system of alkenes. Because we have 1 sigma bond and 1 pi bond, we have this huge, soft cloud of electrons above and below the plane. Now, an acid is going to donate a proton, isn't it? That's what a Bronsted acid does. Proton is positive. Where do you think it's going to go? Well, right smack in the middle of this little cloud of electrons. We refer to this as a protonated pi cloud. So here's our pi cloud, single bond, here's our pi system, and the proton just comes and sits on top of it. Now this is a very, very transient species, but by looking at it, you can understand how we get more or different products very, very simply. So let's start off with this guy as an intermediate. There are 2 things that could happen. This proton could slide over to this carbon, or it could slide over to this carbon. Now when it does, that's going to leave one of these carbons positive. The 2 directions, if we slide over this way, we have this carbocation. Carbon has 3 bonds, therefore it must have a positive charge, formal charge. Over here we slid the proton this way, here it is, and this carbon now has the positive charge. Once again, when we make this or run this reaction, the only product we get is going to be derived from this carbocation. What happens in the second step is that Br minus will attack the positive center to make the product. Now, why do we get only this and not this thing? Very, very simply. This is a more stable carbocation. More stable carbocation than the primary. In the next chapter, we'll talk about carbocation stability a lot and explain why this happens. But the fact that the secondary carbocation is more stable than the primary drives this reaction this way. And our only product is derived from this carbocation intermediate. This we will call Markovnikov's rule. Markovnikov was a Russian chemist, and he described this thing in different terms than I will. What he did is he looked at your starting material, and he said whichever carbon has the most hydrogens, that's the one that's going to get the hydrogen. So this is paraphrases in the has gets sort of stuff. So this has 2 hydrogens, so it will get the third. This guy has 1 hydrogen, it doesn't get it. Markovnikov's rule is probably best understood just by simple carbocation stability. This is a more stable carbocation than the primary is. And again, we'll talk about that in the next chapter. Markovnikov's rule. When bromide adds to the most stable carbocation, that's when we get our product. So this is how we show a mechanism. Our first step, we're going to protonate the double bond to form the carbocation. In the second step, Br- is going to attack to form the final product. Any question on the concept? We'll do this a lot. It'll make a lot of sense later on. Let's just do an example of an elimination reaction. This is a real example. You actually do something very similar to this in lab. This is tert-butyl alcohol, or 1,1-dimethyl ethanol. If we take this in the presence of sulfuric acid, we're going to make an alkene. Now, in order to show a mechanism for this, what you want to do is look at the overall reaction and just say to yourself, my goodness, what in the world's happening here? Okay, it's, organic chemistry is just logic. Well, this again is a very strong acid, isn't it? If you put sulfuric acid in water, H2O, what happens? What protonates it to form H3O, right? Well, if you put sulfuric acid in tert-butyl alcohol, well, here's our overall reaction. Again, we form the alkene. But if you put sulfuric acid there, just like we would protonate water, we'll protonate the OH group. Now, doesn't this thing kind of look familiar? It should from general chemistry. This looks a whole lot like the hydronium ion. It looks like water, doesn't it? In fact, it dearly wants to be water. And how can it be water again? Well, it can take its electrons back. If it takes these electrons back, here we go, takes the electrons back, and again we show this with a curvy arrow. This carbon is now going to have 3 bonds, and it'll be positive. Now that's unstable, that's unhappy, so it wants to do something. We've also released our water from our thing here. The next step to get the alkene, what we have to do is take the electrons from one of these hydrogens and move them in to neutralize the carbocation. This can be any base whatsoever. Base pulls this off, the electrons flow back in, and suddenly we have our alkene product. When we write a mechanism, we're going to, again, write simple steps. We're going to show the flow of electrons, and we're going to use this to rationalize how and why we make a particular product. So any question on the concept? This is where we're going with these things. Again, it's just a concept chapter. Well, there's one other concept that we want to address here, and this is the use of what's known as a reaction coordinate diagram. Reaction coordinate diagrams can be very useful in representing reactions, so you can understand all the steps that are involved, etc. We talked about this very simple SN2 substitution. We said the nucleophile attacks the electrophilic carbon, and the bond to the leaving group breaks. We know that this all happens at the same time. When something happens at the same time, we call this a concerted reaction. In a concerted reaction, there is no intermediate. Now, we showed carbocation intermediates before, but in a concerted reaction, there is none. All right, so in a reaction coordinate diagram, what you do is you simply represent the ground state energies of your reactants and your products, and you show what happens in between. For this, it would be something like this. We're starting here with chloromethane and chloride anion. We're going to plot on a relative scale energy going up. We're going to start here at the energetic ground state of our reactants. It'll wind up at the energetic ground state of our products. Now these are the same, so they're at the same energy. In order to get from here to here, we have to go through this high energy intermediate. Now the high energy intermediate is when we have partial bonds from our nucleophile and our leaving group. This is called the transition state. And in this reaction, this is the highest energy point. When you have a multi-step reaction, as we'll see in the next chapter, the highest energy transition state is called the rate limiting step. As it takes the most energy to get up over the hill, then other stuff can happen. So this is what's known as a simple reaction coordinate diagram. If we go back to our movie, now I put in the reaction coordinate here. Again, you can see that when we hit the planar carbon in the middle with partial bonds to both of these, that's the highest energy spot, and that is our transition state. Any questions? How do you make a reaction go faster? Well, if it takes a certain amount of energy to get over this rate-limiting transition state, if you could find a way to reduce the energy of the transition state, it would go faster. This is the magic trick that enzymes use. This is alkylase. It's an enzyme, and it catalyzes an aldol condensation, actually, which you'll learn about next chapter. If we do that particular aldol condensation just by itself, this is what our transition state would look like. It would have a certain energy. The magic things that enzymes do is that they bind the substrate in a very unique way, and they use some of that binding energy to actually lower the energy of the transition state. And that is how enzymes work. That's why you can do very complex reactions with very little energy input. It's the binding energy to this enzyme that lowers the transition state. Kind of neat. All right, let's wind this up with a problem. I mentioned that the problem with free radical reactions and halogenation was that you would get mixtures of products if you had different types of hydrogens. Look at this assortment of molecules. Identify which will only give a single monochlorination product. Now, what we're really asking here, which of these compounds only has one kind of hydrogen atom? Look at it that way, look at the assortment, and just do something to each of the ones that you think only have one kind of hydrogen and would therefore give one product. Well, ethane here. We have two CH3s bonded together. All of these hydrogens are equivalent, aren't they? They're all on a carbon adjacent to a methyl group. So this has one kind of hydrogen. This is propane. One kind is going to be the methyl group on the end. But we also have a CH2 in the middle, and that's different. Cyclohexane. We know that there are axial and equatorial hydrogens, but remember, ring flip is so fast that essentially they're not. They all blur together. So this is going to be one type of hydrogen. How many do we have here? Oh, we have one. Let's see, there's two types of hydrogen. This guy, well, we have these three methyl groups. That's equivalent, right? We have this methyl on the end that's next to a CH2. And of course, we have the CH2. So that gives us three types of hydrogens. This guy, both methyl groups are attached to our triple bond here. They're identical. And finally, over here, we have methyls all the way around our benzene ring, and they're all equivalent. So the ones that would give single monochlorination products would be ethane, cyclohexane, our alkyne here, and our substituted benzene. Simple exercise. Any questions? And once again, if you did a free radical halogenation here, you would get three different products. Two different products here, and the ratio is, then you get dichlorination products and whatever. It gets really, really messy. All right, that's the essence of chapter 6. Like I said, it's a simple little chapter just designed to introduce concepts in nomenclature. We're going to deal here with the intro to alkenes. Now, we talked about alkenes before. We know alkenes are characterized by having a carbon-carbon double bond. This is one in J-mol, which is slowly rotating for you. You'll note, of course, that this is trigonal geometry, trigonal planar. And we have one bond that's a sigma bond, and one bond that's the pi bond. Just by review, we construct the alkane this way. We're going to take the electrons from one s orbital and two p orbitals on each carbon. Here's our carbon skeleton. This is our sigma network that we form from our sp squared hybrid. Because it is trigonal, again, bond angles are 120, and it's flat. We have a p orbital left over on each of these carbons because we only use two of them. So these p orbitals are still on each of these carbons, and they show up like that. When orbitals are next to each other like that, they can overlap to form a molecular orbital. So our little hot dog here with the sigma network in the middle. And this is our pi system. It's a pi cloud. We call it a pi because it's built from p orbitals, and it's above and below the sigma bond. One of these is our sigma bond, and one is just a shorthand to show our pi bond. Any questions? Now, when we did this a while ago, we also said that because these orbitals must line up with each other in order to overlap, that we cannot rotate around this sigma bond. Sigma bonds, single bonds, you can rotate nicely. But if we rotated this 90 degrees, it would look like this, and the overlap integral, it's called, drops to 0 when these things hit 90 degrees. So this is energetically much more stable than this is. So we simply do not have rotation around the carbon-carbon double bond. This gives us the chance to make stereoisomers. These are two butanes. In this one, we have the methyl groups on opposite sides, and we can use the word trans to describe that. On this one, we have our methyl groups on the same side of our double bond, and this is the cis isomer. Once again, these are stereoisomers. They have the same numbers and types of atoms. They simply differ in space. Now we're going to return to cis-trans isomers in just a little bit. But before we do, I'd like to talk about something called the degree of unsaturation. Degree of unsaturation allows us to look at just a condensed formula, a molecular formula, and tell how many double bonds and rings we have in that substance. It's actually fairly useful analytically. If you look at simple alkanes, for ethane, we have 2 carbons and we have 6 hydrogens. Butane, we have 10 hydrogens, 22 hydrogens, 26 hydrogens. This follows the sequence down here of Cn, where that's the number of carbons. The number of hydrogens will always be twice that, plus 2 more. This is pretty much the definition of an alkane. If we look at a cycloalkane, cyclohexane, we have 6 carbons in a row. We're in a ring. Only 12 hydrogens. If this was a regular alkane, it should have 14, shouldn't it? Cyclopentane, the same thing. N5, only have 10 hydrogens and not 12. Well, double bonds are just like this. Here we have a simple alkene, C6H12, this is just like the cycloalkanes, CnH2n. C6H12. When we look at a simple molecular formula, we can decide which rule this is following. Okay? For every 2 hydrogens that you're missing, we say that this thing has 1 degree of unsaturation. Now that's useful if you have an unknown compound and you're trying to figure out what it is. Because a degree of unsaturation will tell you that you either have a double bond or a ring. Well, it gives you something to look for. Very simple concept. Go ahead and look at these compounds. Here is a simple alkene, obviously. If we add up the carbons and the hydrogens, we have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C6H12. If this was an alkane, it would be 14. So we say this has 1 degree of unsaturation. You could also just look at the molecule and say to yourself, 1 double bond, 1 DU. Our next guy here, we have 6, 7, 8, 9, 10. And if we add these up, I believe there'll be 16 hydrogens. Now, if we had a C10 alkane, we would have 22, wouldn't we? We are missing 6, 7, 8, 4, 5, 6, that's better. We're missing 6 hydrogens. We have 3 degrees of unsaturation. Again, just looking at the molecule, we have a ring, that's 1. We have 2 double bonds, total of 3 DU. All right, look at these guys. How many DUs do we have here? Well, let's see. We have 6 carbons in a boat, right? It's a boat. And we've tied the 2 together, the 4 positions together with a 1 carbon bridge. So we have 7 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So by our formula, how many degrees of unsaturation? Well, we have 2. We're missing 4 hydrogens. That's 2 DU. Now I say 2 rings here. What do I mean by 2 rings? This is what is generally called a polycyclic compound because we have more than 1 ring in this molecule. The rule for calculating DUs, just by looking at it, not doing the formula, just looking at it, is to start anywhere in your molecule and trace a continuous path. Okay, that will be 1. That's 1 ring. Then you look at what's left and you connect those back to your main ring. So for this guy, here's my 6-member ring boat. I've connected them together. And now for the other part, I'm simply going to connect these together, and that's our 2nd ring. 2 rings, 2 DU. This one over here is really simple. This is also a C7. It's also an H14. We have 1 degree of unsaturation. Again, you can just look at it and say 1 ring, 1 DU. Now for simple hydrocarbons, this is nice and easy. But remember, we can also incorporate heteroatoms. For oxygen, it's easy. You just look at it and ignore it. Just pretend it's not there. So, this guy, we're just ignoring the oxygen. We have 1, 2, 3, 4, 5 carbons. We have 10 hydrogens and an oxygen. We're going to ignore the oxygen. If this was fully saturated, it would have 12 for our 5 carbons. Therefore, this has 1 degree of unsaturation. Again, 1 ring, 1 DU, and you ignore the oxygen. Over here we have an OH group. We have to count the H, but we ignore the oxygen. This is going to give us C5H10O. Once again, for our 5 carbons, we would expect 12 hydrogens. This has 1 degree of unsaturation. The only element that, sulfur does the same thing as oxygen. The only one that makes things more complicated is nitrogen. For nitrogen, because it forms 3 bonds, what you have to do is take your molecular formula, subtract the nitrogen, and 1 hydrogen for every nitrogen. So we're subtracting an NH from our formula. And that's because nitrogen is trivalent. Oxygen was divalent, that's why we could just ignore it. So for this guy, we have 1, 2, 3, 4, 5 carbons and an NH. If we subtract the nitrogen and 1 hydrogen, we have C5H10. It should be 12. This is 1 degree of unsaturation. Here we have an amine, just with an NH2 hanging off. We're going to do the same thing. We have 5 carbons. We have a nitrogen. We have 11 hydrogens. Subtract the nitrogen, 1 hydrogen, and still we have 1 DU. Any questions? Well, these are way too simple to put on an exam, of course, right? So look at this and tell me how many degrees of unsaturation we have. Now the hard way to do this is to add up all the carbons, all the hydrogens. You would get C25H40 whole. If we had 25 carbons and a hydrocarbon, because we ignore the O, we would expect 52. We are short 12 hydrogens, so this has 6 degrees of unsaturation. Now, can you look at this and see 6? There's 1 ring, 2 rings, 3, 4, 5, a double bond, and 6 are carbonyl. 4 rings, 2 double bonds, 6 Ds. Now the other one that was on the exam is even more fun. Look at cubane and tell me how many degrees of unsaturation we have in cubane.
8.
Well, it's a cube, so people want to say 6 and 8 and stuff like that. If we simply add this up, what do we get? We have 4, 8 carbons. Everybody has a hydrogen. So it's C8H8. If we had hydrocarbon, it would be 18. So actually, there are 5 to use. Now, where are they? Remember the rule. We're just going to start somewhere and connect till we get back. I could do that. Okay? Now I have to start somewhere here and go around back to the ring that we've already drawn. I could do it this way. We could do the same thing here on the bottom, couldn't we? And now we have these 2 carbons that need to be connected. That's 1 more. And these 2 carbons. 5 rings, 5 Ds. That's fun, isn't it? Okay. Let's go on and do our next big thing here. And this is nomenclature. Okay? Every time we meet a new functional group, one of the first things we're going to do is simple nomenclature. We already know how to name alkanes. We're all really good at that. There are just some slight differences that we need to use for alkenes. First of all, in an alkene, the parent chain must contain the alkene. So the longest carbon chain here would actually be here, going up. But the longest carbon chain containing the alkene would look like that. Now the suffix we're going to use for an alkene is going to be E and E, just like we used A and E. So here in our parent chain we have 1, 2, 3, 4, 5. It's going to be a pent, right? And we're going to call it a pentene. Our second step, we're going to number the chain. But here we're going to number it in such a way to give the first carbon of the double bond the lowest number. So we don't look at substituents, we just look at our parent chain, and we give our carbon, the first carbon of the double bond, the lowest number. That means that this is going to have to be carbon 1. We would show this in our name simply by saying this is a 1 in T. Finally, we're going to look at substituents. If you have more than one, we're going to do di, tri, whatever. And we're going to name these according to their position on the parent chain. Here we have an ethyl group on carbon 2. This is going to be a 2-ethyl, 1 NT. All one word with dashes. Any questions? Look at this guy. Find your parent chain, number it, and jot down the name. Well, the parent chain is going to be this guy, obviously. In order to give the first carbon of the double bond the lowest number, we want to start numbering here. Remember, if this was just an alkane, we would have started here, so we had a 2-2. We must give the alkene the lowest number. So this is carbon 1, and this is carbon 3. This is 7 carbons, so it's a heptene, and the double bond is in carbon 3. We also have at carbon 6 2 methyl groups. So just like numbering for or naming for an alkane, this is going to be a 6,6 dimethyl, 3 heptene. Any questions? We also have to indicate the stereochemistry around our double bond here. What we're going to do here is simply trace out our carbon chains on both sides, and we're going to say, are these on the same side of the double bond, or are they on opposite sides? These are on opposite sides of our double bond here. Therefore, we have to include the word trans in our name. Trans 6,6 dimethyl, 3 heptene. Once see the stereochemistry. Here's your double bond. We have 1 carbon chain on one side, 1 carbon chain on the other. Yeah.
Since it's a double bond, shouldn't you name it like diene methyl? Is that what it says there if you have more than one?
Well, we'll see this. If we have more than one double bond, we'll use diene, triene, whatever. In fact, let's do that now. Cycloalkanes. We had a separate set of rules for naming cycloalkanes. We're going to have a slightly different set of rules for cycloalkenes. The major rule is that you're going to define one of the alkene carbons as carbon 1. Carbon 2 will then be the next alkene carbon. So as we number this guy, we could say that this was carbon 1, but then this therefore must be carbon 2. Here we have 2 double bonds, so we're going to use diene in our name. Our numbering is going to go this way. This is going to be a cyclohex, and we have 2 double bonds, so we're going to call this a cyclohexadiene. Double bonds are at carbons 1 and 4. So we call this 1,4 cyclohexadiene. Now, we leave the A in here because you can't say it without it. All right, so that's just why it's there. And maybe some people can, but chemists can't. So 1,4 cyclohexadiene.
Couldn't make that a 1, 3.
Nope. Let's go back. This has to be carbon 1. Other one must be a 2. You must number through the double bond.
Couldn't make, okay.
And if we started here, it would be the same thing. All right, look at this guy. And write the name. Well, right away we know that these are going to be carbons 1 and 2, right? We know that. If we can, we're always going to generate the lowest number sequence at our first point of difference. So the way you decide which of these is going to be 1 or 2 is to just look at the numbering that you would wind up with. If we let this be 1, then our numbers would be 1, 2, 3, 3, 6, right? If we let this be carbon 1, our numbering would be 3, 6, 6. 3, 3, 6 is better than 3, 6, 6. Well, this is how we're going to number it. 3, 3, 6 is a lower sequence than 3, 6, 6. First point of difference here is this 3 versus that 6. And that's what you shoot for. Lowest number at the first point of difference. Now this is nothing more than a cyclohexene, right? So we're going to start off just with cyclohexene. Now because there's only one double bond in the ring, you don't have to put the 1. Because you know that the alkene is carbons 1 and 2. You know that. Now all we have to do is add up our substituents. We have methyl groups at 3 and 6. So this is a 3, 3, 6 trimethyl cyclohexane. Let's make our ring bigger. Go ahead and do this guy. Now, I'm sure your gut instinct is that, gee, we want to go this way, so we have a whatever, whatever, right? But of course, that's wrong. Because our numbering here would be 1, 2, 3, 4 versus 1, 2, 3, 4, 5. So we want to go this way. This gives us a 4, 6, 6, as opposed to a 5, 5, 7. 4, 6, 6 wins. 4 is less than 5. Now we have 8 carbons in our ring. So it is a cyclooctane. We know that carbons 1 and 2, that's our double bond. Don't need to number. We have methyl groups at 4, 6, and 6. 4, 6, 6 trimethyl cyclooctane. How about cis and trans? Do we need to show that this is a cis double bond here? No. Because you can essentially always assume that double bonds in a ring are going to be cis. There is one exception. If you get up to a 12-membered ring, you can actually fit a trans double bond in. But for all practical purposes, everything here is going to be cis. Let's do one more. Well, it's a cyclohexadiene, isn't it? Two of these carbons, two of the alkene carbons are going to be 1 and 2. And again, we have to look for our lowest number sequence. If we let this be carbon 1, our methyl group would be on carbon 2. If we let this be carbon 1, the methyl group would be on 3. So if that was carbon 1, we would have to go around the ring this way. We want to give both of our double bonds the lowest possible numbers. So even though this would give us a 1-methyl, you want to start here and go up this way so that our double bonds are 1, 3, as opposed to 1, 5. All right, once you've decided that, it's fairly simple. This is going to be a cyclohexadiene with a methyl group in carbon 2. Again, our other way, letting this be carbon 1, would give us 1-methyl, 1,5, and 1,5 is bad. Okay. Once again, we saw an example where we had cis-trans stereochemistry, and we've talked about this before. Again, when you look at your double bond, you trace out your chain and decide if they're on opposite sides, it's a trans. The same side, it's a cis. Everyone's happy with that, right? So this guy, quickly just jot down what you would name it. Well, it's a bute. This is carbon 1, so that's carbon 2, so it's a 2-butene, right? Our carbon chains are on opposite sides, so we could say trans 2-butene. How simple can you get? Now, one that was on the test, of course, was this guy. Go ahead and name him. Well, obviously, cis and trans doesn't apply here, does it? It can't. So what would we name something like this? Clearly, if we swap the chlorine and the bromine, that would be a different compound, wouldn't it? So we are going to get to repurpose something that you already know. Isn't that good? You already understand this perfectly. And we're going to get to use the same set of rules again. This is the Kahn-Engel Prelog rules. But instead of for RNS, we're going to do it for E and C. Just like before, we're going to rank by atomic number. The rule is if the highest priority groups are on the same side, we're going to call it Z. If the highest priority groups are on the opposite sides, it's an E. Just like before, if there's a tie, we're going to keep going till we find a difference. And just like before, multiple bonds count as multiples. So this is just our RS rules applied to E and Z. Z stands for zusammen, a German for same side. E is Antagon, which is opposite. Now, I was a student once, believe it or not. It just really struck me as cruel that Z and E were chosen for this. Because if you look at the geometry of Z, it looks like it should be trans, right? And this, they're all on the same side. It should be cis, but it's not, because they're German. Okay? So let's look at this compound here. We want to come up with a name. What we're going to do is look at the atomic numbers of the things that are attached on all sides. Hydrogen is 1, carbon is 6. Carbon is 6, bromine is big. 35 is big. All right, so now you look at the first carbon and decide which is the highest priority group. Well, it's going to be the 6, doesn't it? Look at the 7th, at the second carbon, 35 wins. These two are on the same side, therefore this is a Z. So just like we did R and S, we're just going to take our name and we're going to stick E or Z in front, in parentheses, with a dash, all one word. This is, let's see, I'm probably going to go 1, 2, 3, 4. It's a butene and a bromine in carbon 2. We stick our Z in front, Z, 2 bromo, 2 butene. And again, this looks like a space, but it's not. No space. This is the dilemma that we had. Quickly decide if this is E and Z and write the name. Hydrogen, carbon, chlorine 17, bromine 35. Our highest priority here is the carbon. Highest one here is the bromine. Once again, this is Z. It's going to be 1 bromo, 1 fluoro, propene. We don't need to number our double bond because there are only 3 carbons. It's Z stereochemistry, 1 bromo, 1 fluoro. Here's a diene. This is going to be a 1, 2, 3, 4, 5. So it's a pentadiene, isn't it? We want to let this be carbon 1 because we want to give our double bonds the lowest numbers. So it's going to be 1, 2, 3, 4. Decide if it's Z or Z.
But once before both Z and front,
I'm sorry?
but once before that we just did with both Z, right?
With Z, right? Well, let's see. We have a 1. We have a 6. And we have carbons. But this carbon is attached to 3 hydrogens. This is attached to another carbon here, and it's a double bond. So 3 hydrogens here, 2 carbons, and a hydrogen up here. Our highest priority group is going to be this guy over the methyl group. Therefore, we're going to go like that. And this is E. Go ahead and put it all together and write a name. It's a pentadiene, and our double bonds are in carbons 1 and 3. Attached here at carbon 1, 2, 3, we have a methyl group, and our stereochemistry is E. Let's just do this one. We're going to have a tie here at our carbon, right? This carbon is attached to 2 carbons. This one is attached to 2 hydrogens and an oxygen. Who wins? Here's our tie. We have 2 hydrogens and an oxygen. We have a hydrogen and 2 carbons. Who wins? Just like R and S, isn't it? The oxygen wins. Atomic number of 8. Now we don't know how to name alcohols, but this would be Z. I call this isopropyl because I could. 2-isopropyl, 2-butene, 1-ol. 1-ol simply tells us that carbon 1 here is attached to the alcohol. We'll do this in chapter 17. All right, some nice exam questions here. Write a complete name for this guy. Put in everything you know. It's going to be a cyclohexene, right? If we let this be carbon 1, we're going to have a 1-methyl, and that's going to be good. We're going to have a 1,3 dimethyl. How about carbon 3? If that methyl group was pointing up, that would be a different compound, wouldn't it? Now, you really can't use cis trans here, can you? Because our double bond is flat. So what are you going to use? R and S. Isn't it fun how it all just comes together? Our highest priority group would be our alkene here, then our CH2, and then the methyl. Hydrogen is pointing up. If we look at this guy from the bottom, it'd be going that way, and that's R. See how quickly you can do this stuff now? All right, so we have a cyclohexene, a 1,3-dimethyl cyclohexene, and carbon 3 is R. We don't have to indicate that it's a 3R because this is the only chiral center in the molecule. All right, how about this atrocity? We're dealing with 1, 2, 3, 4, 5, 6, 7, 8 carbons, so it's going to be an octene, right? Where are you going to let carbon 1 be?
On the top.
At the top, because the double bond has to have the lowest number. So it's going to be a 3-octane with a chlorine in carbon 7. How about stereochemistry? For carbon 3, this carbon is going to be highest priority, right? We're going to start here. For this guy, we have a carbon on both, but this is a CH3, and this guy has a carbon attached. So we're going to go like this. And that, of course, is a Z. So it's a 7-chloro, 4-methyl octane with Z stereochemistry. Any questions? Cyclohexene, right? Figure out which is going to be carbon 1 based on your number sequences. Remember, you must number through the double bond. So they must be numbers 1 and 2. If we let this guy be carbon 1, we're going to have a methyl in carbon 1, right? If we let this one be carbon 1, our methyl would be in carbon 2. So we're going to go this way. Now we have an ethyl group, and we have 1, 2, 3, 4 methyls. Very simply, 3-ethyl, 1, 5, 5, 6, tetramethyl cyclohexene. Remember, you don't need to say where the double bond is, because you know it must be carbons 1 and 2. Cyclooctadiene, right? We're going to let carbon 1 be one of these guys. If we let this be carbon 1, we have a 1-ethyl, and that's good. Our double bonds are then in carbon 1 and 5. Go ahead and write the name. Ethyl group in carbon 1, 1,5-cyclooctadiene. All right, 2 more and then we're done. This is the very simple 1, 2, 3, 4. That's going to be a propene, right? Double bond is going to be in our second carbon. So it's a 2 butene. If we let this be carbon 1, we're going to have a 1 chloro. If we let this be carbon 1, we would have a 2 chloro. 1 chloro is better. We also have stereochemistry here. Is this E or Z? Chlorine's going to win here, right? They're both carbons, but that has hydrogens, and this guy has a chlorine. Go ahead and write it. Z is our stereochemistry, 1,3-dichloro, 2-methyl, 2-butene. And the last one here is going to be a cyclopropene, isn't it? We're going to let this be carbon 1 and 2. So we have a 1-methyl. So we're going to have a 1,3-dimethyl. How about this carbon? It's a chiral center, isn't it? Decide if it's R or S. You can just kind of look down on top of this. So the hydrogen is going away from you. These are both double bond carbons, but this has a methyl. So we're going to go this way, and it's going to be an R. So we have a cyclopropene. It's a 1,3-dimethyl cyclopropene with R stereochemistry. Now, isn't it fun to be able to use something you learned last chapter or chapter before and just repurpose it? And don't you feel really smart for being able to do this? All right. Let's do a reaction of an alkene. We've already talked about it. If we take propene and HBr, we make 2-bromopropane. Okay? We said that this was a stepwise reaction. That what happens is we form a protonated pi cloud. And this is an intermediate that most textbooks don't include, to be honest. I think that's a shame because it makes it really easy to see as this thing slides down this way. This way, the products you could get. Two products, the two carbocations look like this. This carbon has a hydrogen and two other carbons attached. So what type of carbon would this be? Well, it would be a secondary, right? This carbon only has one carbon attached, so it's a primary. This product is not observed, only the product arising from this carbocation. Once again, this is Markovnikov's rule. What he actually said was the carbon with the most hydrogens is going to get the hydrogen. That is very simplistic, however, because what you're really looking for are the two possible carbocations, and you want to choose the most stable carbocation. By his rule, this has two hydrogens. It will get the hydrogen. By my rule, this is the most stable carbocation, and that's what you want to shoot for. Now let's talk a little bit about carbocation and carbocation stability. The ordering is really, really simple. This is a tertiary carbon attached to three other carbons. Secondary carbon, primary carbon, and a methyl. Carbocation stability simply goes tertiary, secondary, primary, methyl. And there's a big difference in reactivity among these. Methyl almost never ever forms. It's so unstable. Tertiary carbocations are actually quite common. When you look at a carbocation, remember that this thing has three things attached. There's a p orbital here, but it's empty. Therefore, this is going to be trigonal planar geometry. So in order to be stable, you want lots of groups around it, and it must be planar. Simple example. We saw this compound, our bicyclic compound. If I made a carbocation here, you might look at that and say, tertiary carbon, that's not so bad. But remember, this is a boat cyclohexane, isn't it? So think about its real geometry. Here's our boat. This is not planar, and this is a very, very unstable carbocation. Now, what is it about having carbons attached that makes it stable? Well, it has to do with inductive release of electrons. Alkyl groups are capable of releasing electrons in towards a positive state. This will become important to you when you do chapter 12 or 14 or something like that. It'll become important when you're doing substituents on benzene rings. But this just shows it. This is a tertiary carbocation. And remember, the blue represents electron efficiency. The three methyl groups around here have pushed enough electrons in that we just have a little bit of sky blue in the middle. With a secondary, we have a big blue patch, and with a primary, it's huge. Very stable carbocation, lots of delocalized charge, very unstable carbocation, lots of localized charge, and this guy's in the middle. Now, you can have carbocations that are attached to other things, not just other carbons. For example, if I put a carbocation here next to an oxygen, this is going to be a very, very stable carbocation. And the reason is the oxygen, and basically anything with a lone pair, can move the electrons in by resonance to neutralize it and put the positive charge on the oxygen. This is why resonance is important to you, because it allows you to explain why this oxocarbonium ion is so stable, regardless of the fact that it only had one carbon attached. Chlorine, we could do the same thing. Again, anything with unshared pairs. Nitrogen is very, very good at it. This is called an ammonium ion, IMM, and it's a very, very stable cation. The other resonance thing that you want to remember is something like the benzyl carbocation. Now, when we did resonance chapters ago, we looked at the benzyl group, benzyl carbocation actually, and we said this was stable because we could delocalize the charge. If we start off with this drawn as a cyclohexatriene, and remember, benzene is not cyclohexatriene, it is not. But it's nice to draw it that way because it makes sense. We could move an electron pair in to neutralize this charge and put the charge here on the ring. Again, we could neutralize that by moving these electrons over and move these down. Basically, we have put the positive charge on the benzyl carbon and on these three ring carbons. Spread out the charge, it makes it very, very stable. In general, if you have something like a benzyl, it is always preferred. If you have a heteroatom, that would be next, and then you do primary, secondary, tertiary. Any questions? Now, in the last chapter, we talked about reaction coordinates to describe a mechanism. Let's take the ionic addition, and let's look at, a reaction coordinate for the addition to the alkene. Unlike the SN2 reaction we looked at, this is going to have an intermediate. The intermediate is the carbocation. We're going to start at the ground state energy here, go through a transition state to form the intermediate. The intermediate is going to be our carbocation. Remember, this is increasing energy along this axis. The slow step in the reaction, that is the highest energy transition state, is this guy. It takes a lot of energy to make the carbocation. But once we have it made, it's really reactive. Bromide is going to come along, going to add to it very, very quickly. And when it does, we will go through a low energy transition state to give our final products. This is the rate limiting step because it's the highest energy transition state. And this is the fast step. So this is how you would show a reaction coordinate or a two-step reaction. Any questions? Remember, the higher the energy, the slower the step. Let's look at a movie. This is from the McMurry book, 6th edition. Again, we're starting with ethene. We're going to protonate it to make a carbocation. Going to add halogen to make our product. Step 1, we're going to protonate the pi cloud and then rearrange to a carbocation. Carbocation is now going to undergo attack from either the bottom or the top, and presto, we have our product. Step 1, carbocation. Step 2, final product. All right, let's apply this and do some problems. Go ahead and draw the product of this simple addition. Well, we know we're going to form a carbocation and a medium, right? There are two we could form. We could form this one, positive charge up here, proton down here, or we could form this one. We look at them and say, this is a tertiary, this is a secondary. Who's going to win? Well, the tertiary. So this is the carbocation that will be formed. It is more stable. It will be formed. If you want to do the Markovnikov rule, this guy had 1 hydrogen, now it has 2. Next step, we're going to simply take our halogen, that's bromine anion. It's going to attack the carbocation. And this is our final product, 1 bromo, 1 methyl, cyclohexane. On your next exam, you will probably have 20 or 30 individual reactions to do and draw products. This is where organic gets really fun. All right, look at this guy. Decide where the carbocation can be, decide which one is most stable, and draw the structure of the product. If we put the proton here, we would form a benzyl carbocation. If we put the proton here, we would form a tertiary carbocation. Who wins? Resonance always wins. Benzyl carbocation is resonance stabilized, and it is more stable than the tertiary. Now you'll note that this goes against Markovnikov's rule, doesn't it? because this carbon actually has one hydrogen. Instead of it getting the hydrogen, this guy does. That's why carbocations are better than rules. All right, so we make this. We're simply going to add bromine. And this is our final product. Now you'll note that when I drew these benzene rings, instead of drawing the 3 double bonds in there, I simply drew a circle. That's because that better describes where the electrons really are in benzene. Remember, it's just this assortment of 6 p orbitals with electrons in them, and the electrons are uniformly distributed. If you want to show resonance, however, drawing the individual double bonds is the easiest way. All right, this is what it looks like in an exam. Go ahead and write these. For our first one, if we put the proton on the CH2, we would get a tertiary carbocation. If we put it here, we would get a primary. Tertiary better, carbocation is going to go here. Once we form a carbocation, bromine is going to add, and that will be our product. Our next one, this would be a primary carbocation. This would make a secondary carbocation. Carbocation will form here. Chlorine will add, and that will be our product. Our third one here, this would be a primary carbocation, wouldn't it? And this guy would be benzylic. Benzyl is always better. Bromine will add here. There's our benzyl carbocation. Bromine simply adds to it. And that's your product. Now let's do one more feature of these reactions. Look at this guy. Decide which carbon will give the most stable carbocation. Take bromide, add it to that carbocation. This is a tertiary carbon, isn't it? That's not bad. But this guy is sitting next to a chlorine that has an unshared pair. 3 of them, actually. So our product is going to be this. Now again, the reason is that this carbocation on this center is resonance stabilized. That is, the electrons from the chlorine can come in, and we form this stable intermediate. Now there's one other feature of this reaction. Remember when we looked at the movie? I commented that we had this little carbocation, that because it's planar, the nucleophile could come in from either the top or the bottom, because it's flat. Go ahead and look at this carbocation and draw the 2 possible products. Well, bromide anion could come in from the top side. And when it did, we would form this compound. Correct? Or bromide anion could come in from the bottom side, and we would form this compound. These are enantiomers at this position, aren't they? This is a pair of diastereomers, isn't it? Now, what if you wanted to name these things? We actually know 2 ways we could do it, don't we? We could do R and S on either carbon. That works fine. Or, since we just learned E and Z, go ahead and name these as E and Z compounds. R and S is actually preferred, but we just learned these Z, so let's do that. On our top carbon, bromine is highest priority, right? Methyl is highest priority here. They're on opposite sides. So this is E stereochemistry. Here the bromine and the methyl are on the same side. This would be Z stereochemistry. Now on an exam, I would tell you if I wanted you to do EZ or RS. Now, I said this is a mixture of diastereomers. Do you think that they're going to be formed in the same quantity? Think about the 2 pathways. Carbocation is flat, isn't it? But bromine, which is big, could either come in from the top, like this, or it could come in from the bottom. If it comes in from the bottom, this methyl group is in the way, isn't it? Kind of sticking out there like a little softball or something. Therefore, this is the preferred path. and this is the major product. This is an example of steric hindrance. Steric simply means size. Hindrance means it gets in the way. The methyl group is big and it gets in the way. This is preferred, and this is the major product. All right, any questions? I don't have a clue what lab we're doing this week, sorry. But I'll try to figure that out and let you know. Next week, again, we're going to do chapter 8, which is going to have reactions, just like we've just done, except there will be like 13 or 14 different reactions that we will do in one day. And it can be a little bit mind-blowing. So you might want to look at it, think about it a little bit before next Monday or Tuesday, whatever today is. All right. See you on Thursday to do something.
Yeah, it's like this is